Hello again, this is Galen Pickett, Physics 151 at Cal State Long Beach. So, it is in the ebook, or the physical book, Chapter 11, Section 4 is what I want to talk about, and there it is, the angular momentum principle. So here is the statement of the principle, how the angular momentum of a system can change. So, here's a system, here's my origin, I've got a particle of mass m, there's a force on it, and that force will change the particle's momentum, it'll change the particle's energy. But how does the angular momentum change? Well, let's see how it changes using a little bit of calculus. If I take the time derivative of the angular momentum, that has got to come somehow from the forces from the surroundings. I've got an expression for the orbital angular momentum, so let's see what that is. I've got the rate of change of, and I'll write this, the position, the displacement vector of the object depends on time, and then I do a vector cross product with m times the velocity, which also can depend on time. That's what the momentum is. And now I've got this cross product and two vectors. The usual product rule of calculus applies, so this is equal to d by dt r of t, so that vector crossed with m and v, plus r of t crossed with d by dt, the mass times the velocity, d by dt of the momentum. And this first, so there's two pieces that come into here, and both of these things, I mean, you can't see where the force is coming from either one of those. This one here has got a special name. It's the rate at which the position vector changes. That's just the velocity itself. And the cross product has got the property that I need a vector that is perpendicular to both of these two things, but it's got a magnitude that depends on how perpendicular they are. And these two things are parallel to each other. The cross product of any two parallel vectors is 0, so this first term goes away. The second term, the rate at which the momentum is changing, also has a special name. This entire thing here is called the force. That's just using the momentum principle. Whatever the force from the surroundings is, it changes the momentum of the system. So what we get for the orbital angular momentum is d by dt L is equal to r cross F. And that force is coming from the surroundings. We call this thing the torque from the surroundings. So if you knew what the torque from the surroundings was, it would change the angular momentum of the system. I could do this in an update form. So L final is equal to L initial plus delta t times the torque from the surroundings. And there is no need to keep just the L as the orbital angular momentum. The total L is equal to the orbital plus the spin, plus I times omega. So if I take the time derivative of both of those two things, I get dl orbit dt plus, now if the moment of inertia doesn't change, then this is I times d omega dt. This has a special name. This is called the angular acceleration, and sometimes we'll give it a name. It's got a vector that we give the name alpha, is what that blue thing is. And that is equal to the total torque from the surroundings. The torque from the surroundings can change the spin, you can change the orbit, you can change both of them together. And for an isolated system, the torque from the surroundings is equal to 0. And that does not mean that the orbital angular momentum stays a constant, or the spin angular momentum stays a constant. You've got to have dl dt orbit plus I alpha is equal to 0. So if the orbital angular momentum changes, the spin angular momentum had to change as well. And that's something that we've seen in the momentum principle when objects in the system were trading momentum back and forth. Here, a single object can take orbital angular momentum, turn it into spin angular momentum, and vice versa.